Okay, so let's get started. I'm going to pull up the solution to homework 6.3, which is kind of bizarre given that I just assigned it, but you'll see what I mean. So homework 5.7 is graded. I graded the first submittal to the project. If there's any one, I would say, mistake, which it wasn't really a mistake, but there was some, I guess I would say, fast and looseness with actually specifying the dimensions. Like instead of dimensioning the entire truss, you only dimension like a member. And with some trusses, like the members aren't even. Either like they actually aren't evenly spaced or they didn't look evenly spaced in your schematics. And just making sure that they're fully dimensioned, I think is important. But in the end, I think you all did great. 5.1 or 5.7 is graded. 6.1, I think is still being graded. There's no homework due today, but to be clear, so just so everybody's on the same page, 6.2 is due on Monday, and then homework 6.3 and 6.4 are going to be due Wednesday. Now 6.3 is literally just installing Mastan and make sure that it works. And what I'm having you do is upload a screenshot that shows me that it's installed. And so what I'm looking for, honestly, is, I'll show you. Like, I even opened a notepad. You don't need to do that. But, like, just this. Just show me it running. You know, that's what it looks like when it's running. So you just have it installed and it's running. Screenshot that, upload it. That's all I need. Okay? So I opened a little notepad and said, this is my solution. That's all I care about. Okay? There are two packages that you can install. One of them, if you already have MATLAB on your computer, you can install it as an MATLAB app, and then the other is a standalone program. Either work, but it's Mac and Windows friendly, so you should be able to install it on either computer. The one thing that might happen on Mac is it might show up as an untrusted app because it's like privately developed. But there's a link on course content that'll show you how to go about that. I promise it's not a virus or anything. So. But that's your homework 6.3, is just to install that. Because after the exam, when we come back Monday, I want everybody to have your laptops because we're going to do some Mastan modeling together. So what I'm basically trying to get around is I want to ensure that it works, that everybody's Mastan is working. And if you can install it and run it, it's going to work. So, sound good? Okay. All right. Now today is a little bit movie time. Because we're going to talk about virtual work. And we're going to talk about tips and tricks to make virtual work easier. Okay? Now, to be clear, there's this lecture, I don't want to say it's not necessary, but you could ignore this and still do homework 6.2 and get it right. Only your homework is going to be this long, and my solution might be this long. Okay, so I'm trying to make your lives easier with this lecture. Okay, so to be clear, let's just go back to where we're at. So we're using the method of virtual work. So we're summing up the integrals for our beam, the little m over EI integrals. And what we found during the last lecture is that if we have problems with single moment functions, it's just an integral. But if we have multiple functions or multiple ranges of functions, then we have multiple integrals that we need to evaluate. Okay, so what we have is our real function, our big M's, our little m is our virtual function. It comes from taking all the original loads off the structure and placing a single concentrated force or a single concentrated moment at the point of interest. It has a unit magnitude and we place it in the assumed direction of the displacement. E is the Young's modulus, I is the moment of inertia, and we have our USCS unit conversion factors. Now, personally, I don't think that the concept is really that challenging. I mean, you have a real structure, you have a virtual structure, you sum up your energy, and there you go. I don't think that's difficult. But I think what you might start finding, at least the last example that we did in class, at least probably opened your eyes to this a little bit. This can start to get a little hairy from an algebra and calculus standpoint. There's a lot of just plug and chug or a lot of rote algebra and a lot of simplification that you need to do sometimes to get to the right answer. But there are some tips and tricks that I have that can make your life a little easier when you're assessing these problems. Okay, and I have 4 tips for you that can help you with computing beam deflections. And I'm going to explain each of these in very significant detail so you understand why they are these tips. But if you want the clip notes for this lecture, they are as follows. Number 1, exploit symmetry whenever you can. Okay. In the end, exploiting symmetry can make your life a little easier and a lot of times result in less integration. Okay, that's the first tip. The second tip, use a coordinate system at the free end, okay? The free end of the beam. And so I'm talking about coordinates, so like for example on a cantilever beam, I'm talking about a coordinate system at the free end instead of at the fixed end, okay? And you'll see why here in a second. When you cut a section, always look towards the origin. Always look towards the origin of the coordinate system, every time, okay? And number 4, exploit integrals with a lower bound of 0, okay? If you take into account these 4 tips, you will find that the amount of work that you have to do goes from this to this, okay? And I'll show you what I mean with each one of these, because I have some real examples to show you why this matters, okay? Let's take the very first tip, exploiting symmetry. And so what I mean by that is going back to what we're doing when we employ the method of virtual work. So we're looking at energy methods. And we're doing that to reduce the overall number of integrals, okay? So let's go back to the very end of the last lecture. And in that lecture, we had a beam that looked like this, and I said, what's the vertical deflection at C? Okay, so we have piecewise functions. We're going to have 2 real moment functions, and we're going to have 2 virtual moment functions. But what makes this problem a little weird is the fact that we have this variable cross-section. And we talked about last time practically why you would do that. It doesn't change the functions, like the big M and little m functions are blind to this change in cross-section, but what it does do is it results in 4 integrals that we need to do if we want to evaluate, you know, the entire deflection of the beam. Okay? Now, let's be clear what we're doing here. I accidentally jumped ahead, sorry about that. But let's be clear what these integrals are doing, okay? What these integrals are doing, if we go back to the principle of virtual work, is they are summing up the internal energy in the system, right? Remember Link drawing the bow, right? And so there is a deformation going on, and you set the external work that you're doing for the system equal to the stored energy, right? And so ultimately, these integrals are summing up those U values inside the system, okay? And so what do I mean by symmetry? Okay, let's consider a very basic function. Let's consider the graph of 6x minus x squared. Now, this parabola shouldn't be outside the realm of applicability for the types of problems we're looking at, because that looks an awful lot like the moment diagrams that we see for certain beams, right? I mean, we've seen problems like this, okay? Now, if I wanted to, let's go back to Calc 1. Let's go back to Math 229. If I wanted to integrate this curve, or if I wanted to determine the area under the curve from x equals 0 to x equals 6, that's a very basic mathematics problem. We just integrate from 0 to 6, right? But this is a symmetric structure or a symmetric curve about the line x equals 3, okay? So another way of doing that would be, let's just integrate from x equals 0 to x equals 3 and then double whatever our answer is. That would work too, right? I mean, it would give us the same answer. If you don't believe me, try it, you know? You have your Casio FX 115 ES Plus or similar scientific calculators, integrate that function from 0 to 6, and then integrate it from 0 to 3 and double your answer. You'll get the same thing, okay? What I propose is that we can exploit symmetry in real-world structural analysis problems to reduce the amount of integration that we do, provided that 4 things are true, okay? Now, those 4 things that need to be true is the beam has to be symmetric with respect to the geometry and the boundary conditions. So we can't use this for like overhanging beams. It won't work. It needs to be symmetric with respect to loading. So we have to be able to, the load has to be symmetric. It has to be symmetric with respect to the flexural stiffness. So the beam has to be either has a constant stiffness or it has to be variable in a symmetric fashion, and it has to be symmetric with respect to the point of interest. So what I mean by that is literally taking this problem taking the sheet of paper and folding in half, and it has to be the same on either end. Okay? That's what I mean by that. Okay? Now, here's what I mean. Here's where exploiting symmetry can help. Okay? Let's go back to the old way. This would be the old way of doing the problem. The old way of doing the problem would have 4 integrals. We would integrate, little m1 and big M1 from 0 to 10 and 10 to 22, and then we would have little m2 and big M2 from 22 to 34 and 34 to 44. What I propose is let's only do the first half and take the entire answer and double it. One of the values of doing that is if you actually look at the functions are a lot easier to deal with and a lot easier to integrate. If you go back to what the functions looked like before, here's what the functions looked like before. So by doing it this way, not only am I reducing the number of integrals that I have to deal with, but I'm dealing with the 2 simplest ones. If I have to deal with these, I've got foiling, the integrals get a lot longer, it just becomes a little bit heavier to deal with. Okay? So notice how I took this problem and I made it a lot simpler real quick. Okay? Does that make sense? All right, let me stop for a second and see if you understand this first tip, this tip of exploiting symmetry. And one thing I will say about this is very applicable in the real world. More often than not, us structural engineers try and exploit symmetry in our designs as well. We really try and do that. Sometimes it's impossible, dependent upon the structural conditions, dependent upon the architect demands, and so on and so forth. Sometimes symmetry isn't available to us, but more often than not, we try and exploit it whenever we can because it results in sound, simplistic design, which I like sound, simplistic design because that means it's usually safe, simplistic design. All right, so far so good? Okay, that's the first tip. Now let's talk about the tip number 2, which is origins at the free end, okay? All right, so what I mean by this is I want to recognize that the algebra will end up being simpler if we use what I'm calling the best coordinate system, okay? And to explain this, let's look at this problem, okay? This is a problem that we did in class together, okay? And it was a problem, we had a beam, it was a cantilever beam. I gave you the E value, I gave you the I value. It was 2 kips per foot over a distance of 15 feet. And I wanted to know what the deflection at the free end was. And I believe that the deflection was like 0.9 inches. Was it something like that? Whatever, okay? Now, let me ask you a question. Here's the problem that we did. Now I want you to look at this problem. Is there any real difference between these two? I mean, what I did is I took this beam and I flipped it so that the coordinate system was over here. So now I have the origin at the fixed end as opposed to the origin at the free end. But I'm asking you, is there any physical difference in the problem? I have a beam, a 15-foot long cantilever beam with a distributed load on it. On the right, I have a 15-foot long beam, cantilever beam with a distributed load on it. Is there any physical real difference between the beams? No, it's the same beam. It would be, imagine if the beam was sitting right here, one of it's looking like this and the other is looking at it like that. It's the same beam. It's just changing my perspective on it, okay? Now I propose that defining the origin at the free end is what's going to help. And let me show you why, okay? So this is what we did in class. We got the real moment function and the virtual moment function, and we got little m big M was 1.25 x to the third, and then we integrated that from 0 to 15, and the raw integral was like 15,820 point something. And then we said, okay, so the deflection is that over EI times 1728, and we got this. I think that's what we got, right? Is that matching? Okay, now what happens if we define the origin at the fixed end? Well, if I cut a section and look to the left, I have to consider the support reactions, okay? So if I cut a section and look to the left where I have to consider the support reactions, now the real moment function gets a lot messier, okay? Now the virtual moment function even gets messier. So look at this. Now I have to integrate this. Well, you want to know something wild? If you integrate that from 0 to 15, you get the same answer. Notice how this way is easier than this way. So when possible, define the origin at the free end, not the fixed end. Okay? It will ultimately and most likely result in less algebra at the end of the day. The beam, I want to be clear, the beam doesn't care. The deflection is what the deflection is, right? It doesn't care how we do the math. The answer is the answer. That doesn't mean we need to make our own lives harder when we do this. So when you're defining your coordinate systems, define the origin at the free end. Okay? With me so far? Okay. Now, that leads into tip number 3. Tip number 3, look towards the origin. Okay? This will simplify the algebra a lot when you cut a section by cutting a section and looking towards the origin. Now, I think that it should be obvious that by now that defining the origin at the free end results in simpler functions to deal with. Hopefully it is, after what I just said, okay? But notice how in both of these examples, I cut a section and I look to the left. I cut a section and I look to the left. To be frank, I was kind of cheating a little bit when I'm looking at this algebra. So what happens if I cut a section and I keep my origin at the free end, and now let's evaluate cutting a section and looking to the left versus cutting a section looking to the right. Let's see what happens, okay? Now I want to be clear, let's go back to statics, all right? If I'm sitting down on this table and somebody breaks out the samurai sword or lightsaber and cuts through the table, I fall down, right? And the reason I fall down is because at that point in the table, there were internal forces, internal shears, internal moments keeping me in equilibrium, okay? The beam does not care which way I look. I am going to get the same answer, but it doesn't mean we need to make our lives more difficult. Now, let's take this problem and let's cut a section and look towards the origin, or specifically looking towards the free end. Now, I have a little note here. Recall that the beam is 15 foot long. That's going to that's going to become important a little later. So I cut a section. Now, hold on. I cut a section. This is x. What's this dimension? 15 minus x, right? So just think about that. So I break out my samurai sword or lightsaber, cut, look to the left. Here's what I get. There's the cut, V, M in their positive directions, 2.5 kips per foot going down. Let's sum moments at the cut. So we sum moments. Draw ourselves our little table. Moments going this way, moments going that way. I've got the moment function going this way. Now look at this. 2.5 times x, that's the magnitude of the load, times the moment arm of x over 2. Nothing over here, 0 equals that. By golly gosh gee, there's my moment function. With me so far? Now let's cut a section and look away from the origin. So what happens if we look away from the origin? So here's the origin, let's look that way. So here's what I've got. Notice I've got the reaction over here. I've got the moment reaction over here, the load, shear, and moment in their positive directions. But look at this. Let's see what happens. Some moments at the cut. So what do I got? I got the moment function going this way. Ooh, look at this. So I've got this distributed load. What is the magnitude of the distributed load? The load times the distance. The distance is 15 minus x. And then the moment arm, how far is it here to the center of that load? Half that distance, half of this, right? Oh, let's not forget, we have this moment reaction over here we got to add. What about resisting that moment? Whoop. We got this reaction over here, 37.5 kips times the moment arm of 15 minus x. So watch this. Okay. Woo! Let's see. So we got the real moment function. We've got this hullabaloo right here. We've got this concentrated moment equals that. Break out those algebra skills. Okay, so over here, 1.25 times. First times first is 225. Outside times outside. Inside times inside gives us the negative 30. X squared plus the 281.25 equals Let's distribute this multiplication. 37.5 times 15 is this. Negative x is that. Woo! Let's take care of some more multiplication. So, distribute the 1.25, distribute that, distribute that, distribute that. We have this. Collect our like terms. So the 281.25, the 281.25 gives us this. The 37, okay. So what happens? That cancels, that cancels. So we're left with this. By golly gosh gee. That was a lot of work, wasn't it? But notice we got the same answer, right? So if I go back, we got the same answer, right? That was a whole hell of a lot easier than going through all this. This was crazy. Again, Beam doesn't care. The Beam does not care which way you do this. But that doesn't mean you need to make your own job harder, okay? So I propose that you're going to get the same moment function whichever way you look. But regardless of which direction that you look, looking towards the origin usually results in a lot less algebra. A whole lot less algebra, okay? Will make your life a little easier. So far, so good? Okay. Final tip. Lower bound integrals with, or integrals with a lower bound of 0. What I said when I defined this tip is I said exploit integrals with 0 lower bounds. What do I mean by that? What do I mean by exploiting 0 lower bounds? How do you exploit that? Well, the short answer is you use 2 coordinate systems. Okay? That's a little wild, but not really if you sort of combine everything I've been talking about. Let's consider this beam, okay? And let's say it's got some load on it. I don't care what the loads look like. It doesn't matter, okay? Now, I want to be clear. There is no way getting around computing 2 integrals. You can't do that. I don't care what the loads are on the structure. Because of the fact that it's an overhanging beam, you have this part and this part are going to be defined by 2 separate moment functions. There's no way around it. So you're going to have to do 2 integrals. Just have to accept that. Now, if we can, now let's start combining a lot of stuff that we said. If we can orient the coordinate system to our liking, if we can place the origin wherever we want, why don't we just use 2 coordinate systems? Why don't we place one coordinate system over here and one coordinate system over here? And you might go, what? Why? Why is that helping? You're just making things more complicated, Dr. Mike. Not really. Trust me. It will greatly simplify a lot of the computations that we're about to do. Okay? And I'm going to try and explain that to you with a couple of relative points, a couple relative examples. But the main point is that it allows us to deal with integrals with 0 lower bounds. And why does that matter? Okay, let's recall how we compute a definite integral. We plug in the top number minus we plug in the bottom number. We are generally dealing with polynomials. Okay? What that means is that the plug and chug aspect of the math makes it a lot easier to do when the lower bound is 0. Let's just consider this function that we're integrating from 0 to, let's say, 4. Okay? So what do? We integrate that from 0 to 4. So let's see, we have the integral of 8x to the 3rd. So 8 times x to the 4th over 4, so that's 2x to the 4th. Then we have 6 times x squared, so 6x to the 3rd over 3rd, so 2x to the 3rd, and then 5x. And so we evaluate that from x equals 0 to x equals 4. So we plug in the top number, minus plug in the bottom number. Well, what happens to all that crap on the right? It's 0, right? So all that stuff over here on the right we can sort of ignore, and just this minus this plus that, and we get 4 over 4. And I promise that's not an error. Somebody got it. Thank you. 404. Error. Okay, a couple people got it. I think. Did you got it, right? Okay, then. Error 404. Okay. Now, let me show you what happens if you utilize one coordinate system versus using two. So this beam has, so from here to here, this is from 0, this is 30 feet, and this is 16 feet. So if I want to find the deflection, I'm going to have to integrate at least from 0 to 30 and from 30 to 46. It might be more integrals depending upon what the load looks like here, but at least I'm going to have 2, and so I'm going to have that. But if I use two coordinate systems, what I can do is I propose I can integrate from either direction. So what I propose is I can integrate this way from 0 to 30, and then integrate this way from 0 to 16, okay? As long as I'm fully encapsulating the entire beam and I'm fully summing up the energy across the entire span, there's nothing wrong with that, okay? And so these mathematical functions will be written in terms of, x1, and these will be written in terms of what we'll call x2, okay? So the beauty of this is that both of these integrals now have 0 lower bounds. Okay, and so that will make our lives a little easier when we're performing this integration. Now, the only other thing that you gotta be aware of is if you're using the point slope formula to determine moment functions, you know how we did that for the little m functions on Wednesday? The only thing you gotta be aware of is that if you're using a flipped coordinate system, so here's what happens. Let's say this is your original function, okay? So let's say, you've got your point here and your slope here. Remember, the slope comes from the shear diagram and all of that. So what happens if you flip the coordinate system? So let's say you have a mathematical function that looks like this, okay? If you flip the coordinate system, okay, but the function stays the same, what it ends up doing is flipping the slope. Because if you took this entire function and flipped it back to the way that the coordinate system originally was, you'd be reorienting the slope. So all you have to do is just make sure that if you're dealing with a flipped coordinate system, whatever your slope is, change the sign. So that's pretty much all there is to it. I'll give you a very quick and dirty example of what I'm talking about. The slope keeps the same magnitude, but it changes the sign. Let me give you a quick and dirty example of what I'm talking about. So right, and I think we had something like that, right? And so we said, here's your shear diagram. So right, and then this is that, right, and then we said okay, and this is that 0 and 0. This was a virtual structure that we had in our last example, am I right? Okay, so if you wanted to exploit a lower bound integral with 0, right, you might place a coordinate system right here and a coordinate system right here, right? So we'll call this x1, y1, x2, y2. So for your m1 as a function of x1, the slope is going to be 2/3. The point is going to be 0, 0. So therefore, m1 is going to be 2/3 x. That's going to be from 0 to 10. Is that a fair statement? So for m2, Okay? So, what's the slope of this line? Originally, it was minus 1/3. We're going to say it's plus 1/3 because we flipped our coordinate system. So the slope is plus 1/3. So I'll say flipped. And then, but here's the cool part. The cool part. What's our point? What are the coordinates of this point right here? If we're talking about that coordinate system, 0, 0. So now M2 is 1/3 x2, and the limits are from 0 to 20. The only downside is that you have your real moment functions have to be done the same way. So that's what I mean when I say flipped slope, that if you're flipping the coordinate system, the slope changes sign. It's the same magnitude, but it changes signs. So. All right, let me stop for a second and see if this makes sense. So I think a couple of you came out to see me yesterday about like the integration. You were having a hard time setting it up. Now you probably see why I said just wait. You'll see what I mean. There's some bigger ideas that probably will make the homework go by a lot faster. Math's fun when it's useful, right? Sorry. I'm an engineer at heart. I can't help it. Okay. Let me stop for a second and see if you have any questions. Did this help clarify some things on the homework? How many of you had already tried like doing a lot of the homework, like a lot of the functions? I know a couple of you did. Had anybody? Did you start to run into like algebra nightmares? Mm-hmm. Okay. Is this making you rethink it a little bit? Yeah. Okay. Hopefully, yeah. Now, one of the things is I gave you some hints on the homework on like how to do some of the problems. But I don't think those hints were completely explicit. In other words, there's still a little bit of wiggle room as to how you choose to do some of the problems. But in the end, it shouldn't really matter. You should get the same answer. Beam doesn't care how you do the problem. The answer is the answer. So, sound good? Would you like another 16 minutes of your life back? Okay. I'm going to pull up the code one more time again, make sure everybody got it. Y'all have a wonderful weekend.